So we have talked about linear motion. We have talked about rotational motion. We have talked about objects that stand still. And now we're going to talk about periodic motion or oscillations, which means that our motion is going to repeat itself over and over and over and over and over again. So one example of this is a pendulum, right? And the pendulum just keeps following the same path over and over again. It starts over here, goes all the way to one extreme and comes back. And that's one cycle. And it'll just keep doing the same thing over and over and over again until eventually friction overpowers what's going on. So if I had a really good pendulum, it would go forever. Okay. Another example of that, which is something we haven't done yet, is a mass on a spring. And when I pull the mass down, if I pull it to here, let's see if I can find a useful length here, okay, it'll keep coming back to that length or that height. Okay, again, until the friction wears it down, air resistance, all those things. Okay, but it'll go from here up to here, and it'll oscillate around this point in the middle. So those are the types of motions that we're going to be talking about when we're talking about periodic motion or periodic oscillations. So if we're going to be talking about something that repeats itself over and over and over and over and over again, we probably want to talk again about period. Exactly. Okay, which again, just so that we can make sure everybody's on the same page, is the time for one cycle, or one oscillation, or one complete trip, however you want to say it. And so this has units of time per cycle. So usually we measure this in seconds, and it's implied in the definition that it is the amount of time for one cycle. Okay. What's the flip side of period? The literal flip side of period. Frequency. And what's frequency? It's the number of cycles per second. Or the number of cycles per time. And what do we measure frequency in? Hertz. Which we abbreviate HZ, I'm sorry, which is 1 per second. So that's just vocab. And you know those things. We were all here for freshman physics. This was like the first thing we did in freshman physics 3.5 years ago. Okay, and it should all come back to you. So, like all the other motion that we've talked about this year, we've always had an equation that we use to express that motion. And for periodic or motion or oscillations, we're going to have the same thing. So I know that I've got, let's say I'm going to take a mass on a spring, and I know that it's going to oscillate between two positions, which are going to be like plus xm and minus xm. And my motion's going to go back and forth between those two. So when I write the equation for the position of my object, of my oscillator, I know that I have to have an xm in there because it has to be between plus or minus xm, right? Okay. And xm is this maximum displacement from 0. But what kind of a function can I multiply by that so that I know that I'm always going to be between positive xm and negative xm? What effectively oscillates between plus or minus 1? A sine or a cosine function, okay? Because those are going to oscillate between 1 and minus 1. And so we say that simple harmonic motion, which is what we're going to talk about in this chapter, is described by this equation, where x of t is equal to xm times cosine omega t plus phi. We'll talk about what all those letters are in just a sec. Sometimes we talk about a simple harmonic oscillator, or an SHO, which is the object that undergoes simple harmonic motion. I will probably use SHM and SHO interchangeably. And that is an omega, not a W. Okay. So XM, which is that maximum displacement from 0, is what we call the amplitude, which again was something that we played with when we did periods and waves and stuff freshman year. T is time. Those are the easy ones. Omega t plus phi is what we call the phase of the motion. And omega is the phase constant. I'm sorry, phi is the phase constant. And omega is what we call the angular frequency. But it will kind of end up relating to things. Sometimes we'll use it as angular frequency, sometimes we'll use it as angular velocity. It'll end up having the same value, and if you think about it, it's kind of the same idea. Okay. So we'll talk more about the phase constant, but effectively what the phase constant does is it shifts my cosine curve. Okay. So if, for instance, I decide that positive is up, okay, then when t equals 0, what's the position of my object? It's not rotating, it's oscillating. But it's by definition where? Is it ever going to go any higher than this? No. So it's by definition at what? It's by definition at xm, the maximum. Okay? So I'm saying when I do this that at t equals 0, x is equal to xm. Okay? And then it goes back and forth. All right? And that works if phi is equal to 0. Yes? Okay. But what if positive is still up, and what I do instead is I stretch it down? Now what's its position at t equals 0? Negative xm. Okay? Now I can't let phi be equal to 0 because the cosine of 0 is 1, but I need this to be negative 1 when t is equal to 0. So what's phi going to be in that case? So the whole thing would have to be equal to pi. This is already 0. So yeah, so your phi would be pi. So what the phase constant does is it shifts the sine curve to accommodate the circumstances where you let t be equal to 0. Because I could set this into motion, and then I could decide to start my stopwatch when it was at the equilibrium point, when x was equal to 0. And then I would need phi to be pi over 2 or negative pi over 2, depending on what happened next. Okay? All right. So we should probably try to relate this to periods, since that was one of the first concepts we talked about. So inherent in this whole idea of periodic motion or simple harmonic motion is that the motion repeats itself after every period. So if I started by pulling my mass down at t equals 0, when t is equal to capital T, my mass should be back down at that negative amplitude. Okay? Because the object is exactly where it was a period ago. So for the moment, we're going to make life easier and just assume that phi is equal to 0. I can start the clock whenever I want. Okay. So I've got xm cosine omega t is going to be equal to xm cosine omega t plus t. Okay, because I'm just substituting in what my times are. So I can play around with a little algebra, and basically what I need is omega t to be equal to omega t plus t, right? So that my angles are the same for my cosine. So this is omega t is omega t plus omega t. Now, how long, when's the first time that cosine repeats itself? Yeah, but how many like radians does it take for cosine? What's the period of a cosine function? What? 2 pi. So this would be omega t plus omega times 2 pi, right? And if I just look at this part, because really what I want to find is t, right? Capital T. Oops, wait a minute. I did not mean to do that. That should just be, whoa. 2 pi. I'm sorry. Because it's the fact that I want the whole cosine to repeat itself. So if I go back up here where this is omega t plus omega t, I need the whole cosine function to repeat itself. So that's going to be 2 pi. What's what? Don't worry about what omega is equal to right now. It's the angular frequency, but I don't really need to know what omega is. What I need to know is that if I look at cosine omega t plus omega capital T, and I want this to be equal to this, okay, then my whole cosine function repeats itself every 2 pi, just like you showed me on my little demo there, that it's going to come back to the same value after 2 pi radians, or 2 pi whatevers. Okay, so effectively what I'm saying is that this omega t has to be equal to 2 pi. And if omega is the angular frequency and t is the period, then the period is going to be 2 pi over omega. Which is something you need to remember. And if t is equal to 1 over f, then I have 1 over f is 2 pi over omega, or omega is equal to 2 pi f, which is something else you need to remember. So there's a whole bunch of new formulas in this chapter. Okay, you with me? Okay, then let's do checkpoint 1. I think maybe we can do it before the bell rings. So that's page 417. If somebody would read that for us, please. All right, so let's just start with that part, okay? Does it really say that when t is equal to 0, x is equal to x, or does it say it's equal to xm? Negative xm, but there is that little m subscript, correct? Okay, which is telling us that it's at its amplitude. So it's like I pulled it down, and now t equals 0, and I've let it go. Okay, and then we want to know where the particle is going to be. So that means we need to know the position. So we have this great formula for the position of a simple harmonic oscillator, which says x of t is equal to xm times cosine omega t plus phi. There's no reason to assume that this is a nice, simple case where phi is going to be equal to 0. But like we talked about with our demonstration here, the phi shifts the cosine function along. So the phi is a function of our initial conditions, which we have up here. So when t is equal to 0, x is negative xm. And if I substitute that in, my equation looks something like that. And then my xm's cancel. So I've got negative 1 is cosine phi. Which means that phi has to be what? What is a cosine of negative 1? This is the part where I get really angry. Thank you, Zoe, for saving everyone. Steri was working on it, I could tell, but it was taking her too long. Okay. So this means that my function is x of t is xm cosine omega t plus pi. And now it's easy. Now I just substitute in my numbers, right? So for part A, t is equal to 2 periods, right? So actually, do I even need to use this equation for part A? No, because where will the object be after 1 period? At the same spot as it started, which is negative xm. And where's it going to be after 2 periods? The same place that it started, because it's moved a whole period. So I've kind of got a guess over here that x of 2t is going to be what? Negative xm. Okay, but I can use my formula. So x of 2 periods is going to give me xm cosine omega times 2t plus pi. But I can't really do anything with that. How can I fix that so I can do something with it? I do need omega. What is omega equal to? 2 pi over t. I bet you that would solve my problem, right? So I'd have xm cosine. I'd have 2 pi over t times 2t. I'm getting rid of those extra sig figs because they're driving me crazy. Times 2t. And now my period, whatever it is, cancels out. And I've got xm times the cosine of what? 5 pi. And what's 5 pi equal to? I'm sorry, cosine of 5 pi, you're right. Negative 1. So I get negative xm like we predicted. Okay. I think we'll stop here because we can use this as a review tomorrow. Yeah, we'll do that. Okay. Okay, and we'll finish up here tomorrow and keep going, but I think we're right on track.